Welcome to The Explainer. Today, we're diving into an absolutely monumental shift in technology. We are looking at how artificial intelligence is finally actually learning the physical laws of our reality. For years, AI has completely mastered the digital realm, text, images, code. But the physical world? That's been this elusive frontier. Well, today we're going to explore exactly how that is changing. And honestly, it's changing fast.
Think about this for a second. A 5-year-old intuitively knows not to stack a massive, heavy block on top of a tiny, fragile one, right? They just understand gravity, balance, and cause and effect simply from existing in the world. But until very recently, even the most advanced billion-parameter AI models completely failed to grasp this basic physics concept. I mean, they could process millions of words describing a falling block, but they couldn't actually predict how that block would fall in physical space.
So let's get into Section 1, the physical AI revolution, moving beyond hand-coded rules.
Okay, to really understand this, we have to look at why traditional AI just totally fell apart the second the real world threw something unexpected at it. Engineers realized they had to move away from rigid hand-coded rules. The solution? It's what we call a world model. Now, instead of just mapping inputs to outputs like an old-school algorithm, these models actually build an internal representation of an environment. It's like a mental sandbox. They simulate dynamics, object interactions, and causality to understand how the physical world really works. So it's no longer just recognizing a 2D picture of a car. It's actually understanding momentum, friction, and what happens if that exact car takes a sharp turn on a wet road.
Moving on to Section 2, the evolution of world models, tracing the lineage of physical AI.
Now, this didn't just happen overnight. To understand how we got here, we got to look at the history, because it actually spans decades of foundational research. Believe it or not, the core concept was introduced way back in 1990 by Jürgen Schmidhuber using recurrent neural networks. But the hardware just wasn't there yet. Fast forward to 2018, David Haw and Schmidhuber revived the concept, and they successfully trained agents to drive virtual cars inside self-generated simulations. Pretty cool, right? But the massive turning point hit in 2022. That's when Meta's Yann LeCun proposed the Joint Embedding Predictive Architecture, or JEPA. That single theoretical framework sparked the absolute explosion we're seeing right now, between 2024 and 2026, leading to massive models like Google's Genie, NVIDIA's Cosmos, and Meta's VJPA-2.
All right, Section 3, Beyond Large Language Models, Textual versus Physical Intelligence.
So, you're probably wondering, wait, how is this actually different from the chatbots I use every day? Well, let's break it down. On the left, we've got large language models, or LLMs. They run on textual inputs, and their whole job is basically predicting the next token, or word, in a sequence. They are phenomenal at language, but they completely lack a true understanding of physics. Now on the right, look at world models. They use raw sensor data. We're talking video frames, radar, LiDAR. And instead of guessing the next word, they compress all this data and predict state changes in what's called a latent space. This is a real game changer because it fundamentally allows them to perform true causal reasoning and long-term planning.
Meta's chief AI scientist, Yann LeCun, really hit the nail on the head with this quote. He says, "Intelligence requires predictive models of the world rather than pure pattern matching." He's basically arguing that an AI can never truly possess intelligence or safely interact with our physical environment if it's just trained to match text patterns. Real intelligence requires predicting the actual physical outcomes of actions.
Which brings us nicely to Section 4, how world models work. Let's look under the hood of physical AI. Let's look at the actual mechanics here. How do developers teach these billion-parameter networks to behave in the real world? It's like a giant puzzle with 4 distinct phases. First up is data curation, and this is huge. It involves orchestrating massive multimodal datasets, like filtering and annotating 20 million hours of real-world video footage. Step 2 is tokenization. This takes all that heavy visual data and shrinks it down into compact, manageable semantic tokens. Third, we have pre-training. This is the magic step where the model's transformer backbone actually learns the physics. And finally, post-training and reinforcement learning. This is where the AI agent gets dropped into an environment, gets rewards or penalties, and figures out how to specialize and plan for very specific tasks.
Now zooming in on that crucial third step, pre-training. Developers basically have 2 paths they can take. On the left, you have autoregressive transformers. These generate the world sequentially, token by token, kind of like how a language model builds a sentence. Because of this, they're naturally suited for cause and effect over time, making them awesome for long horizon planning. But on the right, we have diffusion transformers. These don't work sequentially. They start with pure noise and progressively refine the entire output all at once. And that makes them absolute masters at generating rich, spatially consistent, photorealistic environments.
Section 5. Bridging simulation and reality. Closing the sim-to-real gap.
Okay, so what is the practical application of all this? How does predicting a video frame help a robot make you a cup of coffee without smashing your favorite mug? Well, the biggest roadblock in robotics has always been the sim-to-real gap. An AI would perfectly learn a task in a basic computer simulation and then completely fail in the messy, unpredictable real world. But today, world models are closing that gap. They create physics-compliant, photorealistic digital twins. A robot can run thousands of reinforcement learning iterations inside this hyper-realistic software sandbox. It can train, stumble, fail, and improve without any of the massive financial costs or safety risks of doing it in the real world.
And that leads us to Section 6, Real-World Applications, deploying world models today.
This isn't just lab theory anymore. We are seeing these models deployed right now across major industries. The applications are literally everywhere. Take autonomous vehicles. Companies like Waymo are using models like Genie 3 to simulate totally crazy, rare edge cases. We're talking navigating around tornadoes or highly unusual pedestrian behavior, things a test car might never actually see on the road. In robotics, it's providing the spatial intelligence needed to practice tasks safely. For video analytics, these models are spotting complex industrial hazards and tiny manufacturing defects. And incredibly, IBM is using this exact same architecture to model complex weather dynamics and even analyze genomic data for healthcare. It's just wild.
NVIDIA's CEO, Jensen Huang, has famously compared this explosion of physical AI to the massive breakthrough we saw with text generators. He calls it a ChatGPT moment for robotics. What he means is, we are looking at a massive democratization of this technology. Pretty soon, manipulating and reasoning through physical space is going to be just as accessible to developers as prompting a paragraph of text is today. Just look at the heavy hitters jumping into the ring with highly specialized tools. You've got Google DeepMind's Genie 3, which generates persistent, 3D, interactive worlds at 24 frames per second, just from a text prompt. Then NVIDIA's Cosmos 3 is tackling multimodal physical reasoning and action generation specifically for robots. Meta's VJEPA 2 is doing something called zero-shot robot control, meaning the AI can operate a robot in a totally unseen environment. And then IBM's Prithee model is applying all this predictive power to complex climate and weather physics. Every single one of these tackles a vital pillar of physical simulation.
So, to wrap this all up, looking at everything we've covered today leaves us with a truly profound question. When our digital systems finally master the laws of physical reality, when they can predict and simulate the world better than humanly possible, how will that totally reshape our relationship with the autonomous systems sharing our spaces? It is an absolutely fascinating frontier, and we are watching it unfold right now. Thanks for joining me on The Explainer, and as always, keep questioning the world around you.